Okay, so it seems like everyone who's joining us is already in the session. So I'll continue. So first of all, for those of you who don't know me, my name's Carl Stevenson and I head up DataM's UK operation, and I look after sales, support and service for the UK and North America. Essentially, I've been using Copra RF now since 1994 and a user of Copra FEA2013 now since 2009. Essentially, I'm an open section design specialist, and previously I've worked at two of the UK's largest roll forming companies. And you can find more information from myself and my colleagues at the DataM website. So during today's session, we'll be talking about the virtual roll forming mill. We'll have a brief overview of finite element analysis, and then we're going to look at how we can save time and money with Copra RF and FEA-RF. Then there'll be a brief demonstration of Copra RF 2013 using our new feature FEA-RF roll import. And then we're going to take a look at the new Copra FEA-RF graphical user interface. And after that, you'll have opportunity for a brief discussion and any questions you may have or you would like to ask. So essentially, what is finite element analysis? Well, it's a technique for predicting the response of structures and materials to factors such as forces. And we do this by taking a geometric model and subdividing it into small pieces known as elements. With these elements, we then add a material behavior and some boundary conditions, and from this the FEA software can provide the engineer with deep insights to the behavior of objects. Many of these insights cannot be gained in any other way. Prior to FEA, physical components and prototypes would have to be developed for every concept, and inevitably some bad concepts and some good concepts, but all at a high cost. So if we consider a simple or a linear calculation, such as a displacement and reaction calculation, of course these are relatively simple and they can be conducted on simple 3D CAD systems using a linear method or even a calculator. Whereas within roll forming, these calculations are more complex and if not impossible to solve manually if we are considering the deformation and shape of the form profile. Therefore, what we essentially have now, in essence, is a big calculator doing the work, or the number crunching for us instead, which is defined as a non-linear calculation. So let's now look at how this ties in with roll forming and the progress that we've had in the last 30 years or so. So essentially, the situation circa 1985, we would have a guy working with a drawing board where he would develop a flower, a forming strategy and roll tool design manually. And this would equate for approximately 20% of the overall project or product introduction time. This would be followed by roughly an 80% machine setup, and this would generally be done on a production machine, whereby the new tooling would go onto the machine and some tests would be conducted, and then it would leave the machine to allow for some roll modifications or new rolls to be manufactured. Let's move forward and let's think about circa 2000 now. Well, some 15 years later, companies were now already feeling the benefit of modern software and technology such as Copra RF. We were having a much better picture of the process, and some significant time-saving tools enabled better strain analysis of the flow pattern during profile development. And two-dimensional CAD drawings, for example, will be used as opposed to hard copy drawings. And we can expect to see a 30% reduction in setup. And thus that would lead to roughly a 15% time and thus money saving when developing new roll tools. If we now look at the current situation, now we've been using FEA for some 10 years or more, we are making even further progress. So, with a slight increase in design time for analysis to take place, we're now seeing some significant time and of course cost savings during the machine setting phase. Of course, there is always a battle with higher management when you state there will be some time increase at design to allow for analysis. But ultimately, we are then talking about a 40% time saving in comparison and of course the associated costs with that. And clearly, in the last 30 years or so, role profiles, as we all know, have become more and more complex. So if we consider the conventional role product development process, formally the conventional product process, you would develop a forming strategy, conduct a role tool design, manufacture your role tools, and put them into operation for trial and verification, as I mentioned, generally on a production machine. With this approach, if the quality of the final product is not acceptable for any reason, then the additional cost, time and effort certainly increases significantly, albeit for replacement roles, modifications to roles, as part of a new strategy or production delays, and any production delays that could be caused. So now let's consider the product introduction using CodeProd technology. First of all, we use the software to develop the new forming strategy, consider strain, and we look at our role tool design, and then we verify that strategy and role tool design with finite element analysis. This approach does save significant time and cost compared to the conventional process, as essentially there's a vast reduction in rework and re-engineering involved. Let us also consider the ideas of using different strategies, for example. With the traditional design approach, you'd have to use the strategy you think beforehand is the best one. Previously, due to the associated cost of trying new or alternate ideas, they're quite often left to the side and not considered during the design phase, as a preferred or known examples are used which may not be the best solution for us. Therefore, for this reason alone, quite often they will generally be reconsidered only when there are problems at the machine. So when the costs are at the highest to implement a new strategy. With FEA, for example, different ideas and approaches to a problem can be tested and verified and thus quantified before role tool manufacture. So if we consider the strategy we see here to form the profile, and then ultimately this detail here as an alternative. So the best strategy can then be selected to suit the requirements of the design, machine, and ultimately customer to give the best quality, and ultimately for very little cost. So now let us consider strategies to solve a quantified problem that normally we wouldn't find till we were at the rolling machine with the roll tools installed. Let us imagine this example whereby we have 35 degrees twist per meter. What would be the solution at the machine? What would it cost to solve? And who ultimately will pay for the changes? And of course, how long will it take to implement these changes? And from former experience, whose idea would we try first? Generally, there would be a team of guys all with a different approach and idea on how to solve a problem. So let's imagine we're presented with such a problem. With FEA, we can now test multiple ideas and strategies to find this best solution. And quite often we'll find a solution that we would not normally even consider. This is to give the optimum result and at the least cost to everyone concerned. And quite often it's in the quickest time too. And you can see here ultimately the strategy that we selected, we're able to achieve 0.75 That's 0.75 degrees twist per metre, obviously drastically reduced, and no roll tools are manufactured at that stage. So with the traditional approach, the roll former is very much a black box, and only assumptions can be made upon the problems and behaviour we're seeing in front of us, with no true idea of what's happening. Whereas when we're designing with FEA in our toolbox, the possibilities are much different. We now have full access to the process, and we can gather an understanding of what is actually happening within the material. We can determine the forces acting upon the strip, any elongations that could be caused by these forces, and we can obtain a true three-dimensional view of material behaviour that are actually taking place and happening during the forming process. We can even quantify these problems, and solutions normally are only encountered at the machine. We can establish what's actually causing it, not just surmising what is happening. So we can solve these problems based upon facts. So as you can see on the example on the right, the upward material movement in this area, for example, is causing some oil canning in the base of the profile. When we consider high forces in this area of the profile causing elongation, you can see the effects of the flare after the cut-off process. So ultimately, problems like this we can solve in the virtual world. So, as I mentioned, the process improvements carried out directly at the machine are associated with high cost. This is a known fact whenever we retrofit anything to a design. So certainly when we consider the tool in its most expensive state, following manufacture, heat treatment and hard turn, for example. So quite often verification being conducted on production machinery, again, this is also at a premium cost. So when we conduct these design improvements and process upgrades within the FEA environment during the design phase, these costs are minimised, and ultimately now there is no knock-on effect to these other areas, and no new tools have to be manufactured or modified accordingly. So when there are limitations at the machine, this ultimately doesn't result in a costly failure, because we can resolve it within the virtual world, ultimately driving down costs. So let's try and put some numbers to that. Clearly, I'm being a little bit conservative, but for the profile we were just looking at, it's estimated that if we were working in the traditional method, the rolls to be substituted alone would have cost circa €7,500. And with that, the labour costs for testing, roll manufacture, replacement and so on would be circa €5,400. Let's now consider the weighted sheet material. Of course, maybe we got the strip width incorrect in the beginning, and we had to take a minimum order quantity from our supplier. So this would have cost circa €2,000. Then we have the associated cost, the loss of opportunity. This could be while our production machine is not producing new profile or existing profile for our customers. Overall, this is roughly €55,900. When we now compare this with a modern technique with using FEA to drive down the design phase costs, we have software amortization to consider. We have a negligible or no hardware amortization to consider. And then for the time of the project, we have the labour cost of the technician, the role designer and finite elements analysis engineer, who's now doing all of the work in the office. So this cost is €5,200. Ultimately, for this particular profile, there was a €50,700 cost saving. So if you imagine if you're manufacturing 10 or 20 roll tool sets a year, and you're presented with these same problems, the savings you could make. So now I'd like to talk about a few of the new features. We now have the possibility to very quickly and easily import projects and roll drawings, designs from third-party software. and legacy data, thus making it easy and possible to verify your design and strategy with COPA FEA-RF. So using our new and simple import tools, it's now possible to import flare patterns and roll geometry directly into the COPA environment. So this then allows organisations and individuals access to COPA technology and the possibility to adopt the complete COPA workflow during their product development stage. So thus, you can optimize and verify flares and strategies and roll tool designs prior to roll tool manufacture in an easy-to-use COPA environment, ensuring optimum quality and right first-time results. And finally, just a brief overview now of our new graphical user interface with COPA FEA-RF 2013. Well, as we all know, we have a tailored menu system specifically for the roll forming application, which remains, and all of the existing COPA features are still available and valid within the FEA-RF 2013 menu system. But now we have a Windows user interface, which are ribbon and icon driven. And we can now increment with station numbers, have the possibility for multi-window display to show models and diagrams, and we can have single view display of menus, and we have a complete menu history, where we've been and what we've been doing during our post-processing efforts. So now I'll give you a demonstration of that and essentially how it works from beginning to end with CRF 2013 and FEA-RF 2013. Okay, so I'm in a project right now and I have to create a new parametric project. So go to CAD Finder and do so. So once I've created the project, I don't need to do anything more other than go into the COPA tab on the ribbon and select Project Import from the FEA-RF Import tab. And now I have a project here from another software vendor. And at this stage, we'll now convert this project into a parametric format to populate our spreadsheet with all relevant entity and unfolding data, as you can see here at the bottom of my screen. And thus the flare is then imported. If we go to the Roles menu, we can also see these in here too. And you'll see now in CAD Finder, the horizontal centers 300mm have also been assumed with the project. You'll see that the roll numbering is also remains the same as the source project. And now, of course, we can use COPA to check for collisions between rolls. And once we're happy with that, we can now go to the punch sheet editor and add some holes. So now I'll insert a row of holes. And now we can create a 3D model with those holes. So now we've very easily and very quickly taken a project and added some holes to that. So now we can see our holes. Within the roll train. From here now we can create a finite element model. So if I go to our simulation tab and now create an FEA project with the COPA FEA RF project manager. Put some brief details with regards to the project. And now using COPA to FEA, the beginning of our pre-processing, we can specify our mesh detail. We can automatically mesh our holes. We can select a material, some properties. I'll just take a standard. Specify a coil length, and you can see here the station distances we have, which came through from the import. We'll add some flat strip supporting rolls, and we'll also consider stress relief. At that stage now we can hit run project, and we just wait for the new Mentat interface to start. So now we can see our roll tools and model within the FEA environment. So at this stage, the workflow, as I mentioned previously, has become ribbon-based, and here you can see the FEA RF tab, and then ultimately the subsequent Mentat tabs. We're going to be looking specifically in COPA FEA RF, and in here we have the possibility now to edit the model, add chamfers for example, and consider length cut. If we want to modify our mesh in any way, we can do so here. In exactly the same way as we could before. If we're conducting any restarts, we have the restart functionality here. And of course, if we're defining the friction model, running the simulation is done via here, where we just specify how many cores, for example, we're using, and so on. So, as it would take some time to simulate, we can now go to one I made earlier, as it were, open an existing project of the same profile. So first of all, let's discuss what's available within the utilities here. Well, if we click on Station Browser, you can see we have the existing browsing tools from COPA previous menu system. And we have the view controls in here for front, top, left side, ISO and top views with the pull down menu. So these are the traditional menus, and of course now the show menu, what we would like to see, the strip rolls, etc. And then within utilities, we have a combination of those. Well, what we have now within this environment, we have view controls, which as I mentioned are icon driven. So if we zoom in here, you can see now we can show the nodes and we can switch them off directly. We can hide the strip if we would like to. Switch it on. We can make a wireframe of the strip, or we can fill the strip. Exactly the same now with the rolls. We can switch all of the rolls off or on at the click of a button. And of course, if you would like to fill the rolls, we can do so. And if you would like to make a fine fill in exactly the same way, we can do that there. So model results, for example, is now sitting here under the icon, so we can see the model, or we can see graphs, plots, longitudinal strain and thickness, for example, here. We take a quick look at visibility. We're all familiar with this browser, which is formerly under selection. We can deselect all, and we can switch on just a few stations if we wish. Okay, so now we have the scan tools, as we're all familiar with too, where we can flick through, but we have station specific now in here. And although we have the Mentat browsing tools along the bottom, we have some COPA specific tools, or should we say role forming orientated browsing tools across here. And now if I'd like to select displacement, stress or strain, we can switch on the contour bands. We can change our settings here, or our range settings in here. And let me just show you the menu history. So if I go here again, I can go back. And let's talk about strain in the Z direction. We can make some setting changes now. We no longer have to wait. And of course the dynamic tools now are all happening under the hand here, where we can zoom in as we could do previously. If you want to zoom in a specific area, we can save the view. And of course now if I go back here, I can then get the view to take me back. To give isometric views, we can use this possibility for front, top, bottom, left, right, and ISO 1, 2, 3, and 4. And of course some favorites along here. So let's just fit this in to the screen. So now we can browse forward through a station using icons, and of course backwards. We can go to a specific station. We can go to the final station, and of course we can then monitor the results file from here. So now you can see we've imported the profile from a third-party system. We've added holes to that with Copra RF. Very quickly and easily created a model and now simulated it, and we can see the effects within our environment. As I mentioned previously, now we have the possibility for split windows. So I'll just go back to the beginning now. And switch on the nodes, and I'm going to conduct a longitudinal strain plot from a node. So now I'll go to plot from node, select the node here, and we have to wait a few seconds for the longitudinal strain plot. I have a question here. Can we check the loads at the roller's axis shaft? Yes, of course. I'll show you that just now. So now we have our longitudinal strain plot visible in our window. We can now go to Wind Cascade, and of course we can select the windows we would like to see, and we can tile those windows. So now we can see we have multiple window environments, and here we can see we have some remaining elongation, quite high levels at station 4. So we can go back now to station 3. So if we highlight the model, go to a specific station, and we can fit the window over there, switch on our rolls. We can now observe the remaining elongation at strip edge, and what's causing the problem here is clearly the side roll. So in answer to the question now, I can minimize this window, maximize this one. If I want to consider forces, this is now under displacement, stress and strain. So I can look at contact forces here, forces normal, which is now of course measured in newtons. I have to change my settings, change them back to automatic from the range, and now we can see the load acting upon a station. What I always like to do in an advanced plot, I just make these elements invisible, and also these surfaces, so there's no influence on this scale. Now if we'd like to consider this for deflection, forces acting upon the axes, and now of course we consider shaft deflection. So let's imagine we specify, I guess, 2 inches. We have a length of I think 350 would be suffice, and now we can plot those, and ultimately if I click OK, we can now file those in here, close down those, and there we go. So we can have the plot adjacent to the forces. So hopefully that answers your question. So what are the typical outputs we go through during the post-processing? Well, for myself, and it's a question I'm asked quite often, as a minimum, I would certainly look at displacements in the beginning in the X and Y direction. But for myself, I actually achieve and find the most from strain in the Z direction, looking for elongation. And ultimately, if I see some high elongation or remaining elongation, which is relevant to the longitudinal strain plot, I will then observe this and look at forces, again looking for high forces, where the forces is coming from and what could be causing the problems. And then the next stage, which I'm just about to go to, I would conduct cross sections. So I've plotted from node, I'm just going to plot from element now. So let's take a plan view of the strip. Select an element here. And all of the time when I'm taking cross sections or plotting graphs, I'm adding them to my report. And this is in exactly the same way. So we can say and of course now we create a report in exactly the same way. Okay. So essentially you can see now the user interface is much different, but the functionality is certainly all there. It was available before with some new added functions. Of course, we now have the measure functions. We have access to the calculator directly. We can go directly to the FEA project here via the file browser system. We have some nice controls now if we want to see domains, for example. Let me just show you that. Under identification control or boundary conditions, we can switch them on and regen them directly in here too. So this makes things much easier to access. So essentially, as far as the demonstration goes, you can see now the post-processing techniques and report management is the same. So I guess at this stage now, so please feel free to use the chat window for any questions. And of course, if you think of something later, you can please email us at datam@datam.de and we'll endeavour to answer those for you.